Okay, this is business math, or business calculus, math 1316 for our class at LCU. This is the Tuesday, November 3rd, 2015 lecture. If you're one of my students, you'll want to go on our class website, rejoicealways.net, and download the logarithm exponential applications handout. I'm going to be working a couple of problems from this, and you should be able, by the time you, if you look at the, one of the examples on the handout, example 2 is just like problem 43, and, or example 5, excuse me. And you should be able to understand that. I'm going to work problems 46 and 48, and then another application problem. So if you want to pause the recording and go to my website and download that handout, so you'll be looking at what I'm looking at, that'll be fine. But we're going to be using our rules that we learned in class Thursday for taking derivatives of logarithm and exponential functions, and just see a few simple business applications with them. So I'm going to be working number 46 off of that handout first. And on number 46, we're given a supply function. And so I'm going to erase the stuff at the top here to have a little more room to work. And the supply function is P is equal to 10 plus 50 times the natural log of 3x plus 1. And we're told that x represents how many units of a product are being supplied, and the price at which it'll be demanded is P dollars. And so we're asked to find several things. Part A, find the rate of change of the supply price. Well, all that is the rate of change is just the derivative, so P prime. And so you're going to take the derivative of this using our rules for derivatives that we practiced in class on Thursday. The derivative of a constant is 0, so you just leave that blank. If you have 50 times a function, then the derivative of a constant times a function is just the constant 50. Now, what is the derivative of natural log of a function of x? Well, it's just f prime of x over f of x. So it's the derivative of the inner function, 3, over the function. This is the derivative of the log of 3x plus 1. You can go ahead and simplify it just a little bit. P prime is equal to 150 over 3x plus 1. Now, that's the derivative. It's the instantaneous rate of change. If I wanted to graph this function, and maybe you look at the graph of a tangent line to this function at any particular point x, I'd just take that x, plug it into the derivative, and I'd have the slope of that tangent line. Let's see what we're supposed to do on part B. On part B, we're supposed to find the rate of change of the supply price when the number of units is 33. In plain English, that just means evaluate P prime at the value 33. So find P prime of 33, and that's just going to be 150 over 3 times 33 plus 1. This is a real nicely crafted problem for homework or something. If the numbers get hard, we'll use a calculator for the heavy lifting, but 3 times 33 would be 99 plus 1 is just 100, and so it's 150 over 100, and that would reduce to 3 halves. Now, it's a price. I mean, that's an exact answer. It's a fraction, but it's a price. P is the price, and it's the P is the price. P prime is going to be the rate of change of price. So write it as a decimal. It would be $1.50. So P prime of 33, the rate of change of price when 33 items are being produced, the rate of change is $1.50. And let's see if we're asked anything else. Part C, approximate the price increase associated with the number of units supplied if we increase production from 33 items to 34. Well, it's that right there. That's your answer to part C. It's just that evaluated. I don't know if you remember, we've done marginal analysis with things like marginal cost, marginal profit, marginal revenue. Well, right here, what this means is if I'm currently producing 33 items, I don't know what my price is unless I plug 33 into this and evaluate it and see what I get. But if I increase production by 1 item, my price will go up by $1.50. What if I increase production by 10 items? All you do is multiply $1.50 times 10 and be $15. My price would increase. And that's all you're asked to do. That was problem 46 on that handout. And I'm going to ask you to do some that are very similar to that. That's also very similar to example 5 as well. If you look on the website, you'll see which numbers I've asked you to do on this handout. Let's see what the next example I thought would be a good one to work. Well, that might be it. Okay, I'm going to do one more problem, and it'll be similar on this this handout. Oh, excuse me. I'm going to do number 48. Sorry for the confusion. I kind of forgot what in the world it was I was doing. Let's just do problem 48, and you're going to have some homework problems similar to that. Okay, problem 48. This time we're given a revenue function. Again, X is how many, and I don't know if it tells us how many items or tens or hundreds or thousands of items. It says it's X items, X units. So if I produce X items, this gives me my revenue, money in the cash register at the end of the day. And again, I don't know if it's per day or per week or what. It doesn't tell us, but it doesn't affect the way we do the problem. We're asked to find the marginal revenue. Well, all that means is take the derivative of that. Your marginal revenue function is just the derivative of the revenue function. Now, what do you see when you look at this function? And here's what I see. First of all, I see a constant, 1,000. And then it's going to be 1,000 times whatever the derivative of this function is. Well, when I look at that function, what I see is a product of two functions. I see this is f, this is g, and so I'm going to use the product rule. F prime times g plus g prime times f. F prime would be 1 times g plus. Now, for g prime, if you're uncomfortable with doing this in your head, and it might not even be wise to do it in your head, just off to the side somewhere on scratch paper, just say to yourself, okay, g prime would be, think of g as being e to the negative 1/50th x. You always want to think of these in a way that you can make it easy to apply the derivative rules. Well, if I have e to a constant times x, use the chain rule for the exponential function. It's going to be the derivative of that function, which would be negative 1/50th times e to that function. So there's g prime. That's what I'm going to put right here. Notice the negative right there? Negative 1/50th times e to the negative 1/50th x, or x over 50, it's the same thing. That's g prime times f is your function x. So there's your f prime times g plus g prime times f. So I'm going to erase that part. If you are trying to do this or something and want to make some notes, feel free to, but you can always stop the recording and go back to it. Okay, so that, I'm going to simplify that a little bit now. Not a lot, but here's what we're going to do. First of all, I can factor, I see a term plus a term, and I've got a common factor of e to the negative x over 50 to each term. I'm going to factor that out. So I'm going to have my 1,000 times e to the negative x over 50. And then what I'll have left in this first term, I have the factor of 1. I've got a negative sign there. So be sure, don't forget the negative, minus. And I factored the e to the negative x over 50 out, so I have an x times 1/50 to be x over 50. So there's your marginal revenue function for this revenue function. On number 48, that's all they asked us to do. They don't want us to use it. If you were asked to make some conclusions from this, again, x is how many items you're producing. Well, what if I'm currently producing 10 items? Well, find the marginal revenue of 10, and the number that you get is how much your revenue would change if you increase production from 10 items to 11, if you increase production by 1. But they don't ask us to do that on this particular problem. Now I'm going to put this handout down and move to another one. I'm going to pause the recording for just a second. Okay, there's another link on the website, and it's just called Application Handout 2. And what this really is, it's problem 52 on page 715 on the previous handout is what it is. And what I've done is I've just taken it and I've typed up several additional parts to the questions because it's a great illustration of something. And then I took the problem out of the book, problem 52, and that's what we're going to work here. And then there's another page on this handout, the second page. It has a problem, similar function, same type of questions, and I want you to work in. Let's do that for homework. What this is, it's a function that gives us the concentration of a drug in the bloodstream X minutes after the drug has been injected into the bloodstream. And so X is how many minutes after the drug was injected, and C of X is the amount of the drug. Typically on something like this, it's a common way to measure it is in milligrams per deciliter. And so I think that is the concentration that they give. Milligrams per milliliter. And so it doesn't matter. If you get a number like 15 milligrams per milliliter, you can tell if that's more than 10 and less than 20. But we want to ask several questions about this. If you were doing this, some problem, you just wanted to analyze this function, the first thing you ought to do is just get some values. Make an XC table. Use your calculator, like we've taught you in class, and just look at it. Like when X is 0, how much drug is in the bloodstream? It better be 0. Then when X is, maybe 5 minutes or 10, and we won't know until we look at the function a little bit to see how it lasts. But so the first question that I ask on the handout is how many milligrams per milliliter of this drug are in the bloodstream 10 minutes after the injection. And so that's question 1. Well, all you're going to do is evaluate C of 10. And just use your calculator for that. Said if we had any, let me get my calculator. So what I would encourage you to do, since we're going to evaluate this function at several different values, is go ahead and enter this y1 equals on your, most of y'all are using a TI-81 or TI-82, 3 or 4. And the way I would enter that, I'm going to erase this in a moment, so write it down if you need it. But hit your y equals top left button, and y equals 20 times x, hit your x key. And then you just hit your e to the x key, and if you're in math print mode, it'll give you a little box for the exponent. Just key in your negative sign, 0.04x. And then go to table start, table set, second table set. And let's just put 10. 10 for the table start. And for delta table, maybe put 10. So we'll go up in 10 minutes, 20 minutes, 30 minutes, etc. And let's just look at some of the values. So I'm going to use my calculator to do all that. And I would encourage you to pause the recording. You do the same thing and then check your values against what I'm getting here. So I'm going to erase this and just put the answer in. I just go to look at your table and let's see. 20 times x times, oh, I didn't key it in. I was telling y'all how to do it, and I didn't do it. Okay, so in 10 minutes, I get 134.06, and just round it off to 2 places, that'd be fine. That's 134 milligrams per milliliter of this drug. Now, if you look on your XY chart, again, this is not anything the problem asked, but it sure helps to have a good feel for what the numbers mean so that you recognize if an answer that you get is reasonable or not. I'll put the values when X is 10, 20. Let me go down here to when it's 80 and 100. When X is 10, our value for C was 134.06. When X is 20, it's 179.73. When X is 80, it's 65.22. And when X is 100, it's 36.63. Now, that tells us a lot. It tells us, 10 minutes, this amount of the drug in the bloodstream. 20 minutes, the amount is increasing. So maybe it wasn't injected into the bloodstream. Maybe it's just injected into the body, what they'd call a subcutaneous shot, like an insulin injection. And so it has to be absorbed by the body into the bloodstream. But in any case, you have 20 minutes, you have quite a bit more of the drug. But look here, after 80 minutes, quite a bit less. After 100 minutes, even less. And that matches real life experience. If I were to graph this thing, it might look something like this. It would be 0 milligrams per milliliter at the start. It's going to go up to max, and it's going to start tailing off, and eventually we're back down to 0. And so what we would be concerned with this on, and I think it's what I'm going to ask you on this handout, what is the maximum amount of the drug, and after how many minutes will it be in the drug in the bloodstream? And you can see how this would be very interesting, not just to a doctor or a patient, but what if you're the company that's selling this drug? What if you could change a little something that would modify some of the numbers in this equation and make it wait longer before the drug peaks? Or maybe instead of looking like this, it might look like that and peak a lot faster and wear down a lot faster. So those are the kind of things we're going to be interested in learning. So let's see what the next question is. Question 2, just another value. What is C of 120? Now, that's 120 minutes, okay? And just go to table set and set your starting value to 120 and look at your table. And the value of C is 19.75. Okay? And so that tells me 120 minutes, 2 hours. The drug is I wouldn't say it's nearly out of the system, but it's decreased significantly. You might, if you're just curious, try C of 1200, which would be 20 hours. This is 2 hours. Add another 0 would be 20 hours, and see how much is there. You can do lots of things like that. Now, question 3 says find C prime of x. Tell you what, I'm going to erase those two. Don't need them. I might need the room up here on this little bit of whiteboard where I'm recording this. So let's find the derivative. Now, the derivative of this function is going to be the rate of change of the amount of the drug in the bloodstream at any particular time, x. What do you see when you look at that function? Well, I hope what you see is a constant times a product of two functions. This is going to be your f, this is going to be your g, and your derivative is going to be the constant times the derivative of f times g. Use the product rule, f prime times g plus g prime times f. The derivative of x would be 1 times e to the negative 0.04x plus, there's your f prime times g. G prime, e to the function. That would be the chain rule for exponential functions that we showed you on Thursday. It's going to be the derivative of that function, which is negative 0.04 times e to that function. Now that's g prime, all of that. We need to remember to multiply it by f. And now we'll want to simplify that sum. And again, what I see when I look at that, I see two terms. Okay, I'm going to erase my f prime times g business. That was the f right there. And an e, I see a term here and a term here, and when I have factors common to each term is the e to the negative 0.04x. So I'm going to factor that out. That'll leave me with a 1 here, minus, that's gone, but I have the negative 0.04 times x. So there's my derivative. And that's the rate of change. And again, I could do marginal analysis. I could say, what if it's after 5 hours, how much more of the drug is there going to be or less in 6 hours? And just evaluate C prime of 5, and whatever you get, that would be the answer to that question. But what the handout asks you to do is graph this function. Well, how do we graph a function and find all the important points? Well, what we're going to do is take the derivative. We've done that. Simplify it. We've done that. Set that equal to 0. Okay, and again, I'm going to scoot back up here. I'm going to write down that derivative over here so that I have some room to work. I might be getting to the right-hand side of the camera, I don't know, until I look at this. It's getting pretty close, so hopefully you'll be able to see that. Now, what do you do with that derivative? You set it equal to 0, we're going to find critical points. So we're going to set that derivative equal to 0, and we're going to use the zero product principle to find our zeros. Okay, if you have a constant, that's going to add nothing. You have 1, 2, 3 factors being multiplied is equal to 0. The zero product principle says if any one of those factors is equal to 0, I have a solution to the whole equation, because 0 times all the other factors would be 0. Well, 20 can never equal 0, so you just ignore it. Now, this takes a little bit of practice. This is just algebra review. But whenever you see e to an exponent is equal to 0, can't happen. E to a power, e to a number is never equal to 0. If you look at the graph of the exponential function, that's pretty clear. But what it means when you see an equation like this, you're not going to get a critical point from that factor. So that's the key thing. When you see e to the power, no critical point from that factor. Now, that means if you have this factor is equal to 0, we'll just set it equal to 0 and solve. Subtract 1 from both sides. Divide both sides by 0.04, negative 0.04. And that'll give you positive 1 over 0.04. And again, if you had to, you could get a calculator, but just think for a second. 0.04 is 4/100ths, and so this is the same thing as 1 divided by 4/100ths. Well, how do you divide a fraction? You invert and multiply. So see, that's going to be 1 times 100 over 4, which is just 25. So you get x equals 25. That's your critical point. X equals 25 is your critical point. Now I'm going to erase all that work. You've got it. You can back it up and look at it if you want. Let's make our sign chart. I've got x, c prime, and c. C prime is equal to that. I've got one critical point, 25. I'm going to test regions. Well, and again, if you're not used to or familiar with exponential functions, you may want to use a calculator for this. But I'll tell you this, if you put, take a number to test in this far right-hand region, if you put a million in for x, negative 0.04 times a million is e to a big negative number, which is essentially 0, but the key thing is it's never negative. E to a number, it's going to be a positive number. Try it. Just plug a million in for x. A million times negative 0.04, raise e to that, and you'll get a positive number. So this factor is positive. This factor is positive. Now, if you put a million in for this, you have one. Well, if you put 100 in, you'd have 1 minus 400. It's negative. This factor is negative. If you multiply a positive times a negative, that means c prime is negative for all values in that region, which tells me that c is decreasing here. This critical number came from a factor with an odd exponent, and so it's going to flip-flop. The region's going to change sign around a critical number, and that means it's increasing here. And if the curve is going up and then down, increasing then decreasing, that's a maximum. So that's going to be your maximum concentration of your drug after x equals 25, after 25 minutes, or 25 minutes after the injection. Let's find that value. And again, you've really got everything you need to do that. You had the function in your calculator, and just go to table set and set your starting value to 25. And see what you get for C of 25. You get 183.94. That means the point 25 and 183.94 is a maximum value for that function. Let's draw the graph. I'm going to omit, we just don't care right now because the question wasn't asked. What about concavity? How would you discern that or figure that out? Yuck. I'd have to take this thing and take the derivative of it, use the product rule again. And it's not going to be too bad, but it's going to be somewhat ugly, and it's not going to be worth it. Feel free to use your calculator and just look for concavity. But in this function, if I let x equal 0, 0 times the rest of it is 0. So your y-intercept is 0, 0. We have the point 25. If I go to 25 and 50, If x is 25, put 200 there. 25 and 183 be about right there. So you have 200 and 0.25, 183.94, and your graph's going to look something like this. And I might talk about in class, how do I know it looks like that? Well, because if you do the work with your second derivative and concavity, so we are going to have an inflection point here somewhere. It's going to be concave down on the first part. But you will have an inflection point over here where it changes from being concave down to concave up, and you just end up with one inflection point. If you take again, this is just calculus we haven't done, but if I were to take this function, I don't know if you guys remember what a negative exponent means, but I'm going to erase my sign chart. You need that to sketch the graph accurately. But another way I could write c of x is have the 20 times x over e to the positive 0.04x. This is just another way to write the original function. And when you raise e to a number like 10, 100, 1,000, this denominator keeps getting bigger. And eventually it's essentially infinity. And so you might have 20 million over 20 billion. It's essentially zero. And so what that means, the limit of that function, as x goes to infinity, which would be a right-hand asymptote, is going to be zero. Is what it's going to be. That's more than we did in our study of limits and more than you typically do in a business calc class. And just don't worry about it. That's what your graph would look like. Your maximum dosage, amount of the drug in the bloodstream, is 183.94 milligrams per milliliter 25 minutes after you've had the injection. And so again, you can see how that's a real handy application of what you've learned about calculus. And on that handout, you've got another problem that's a similar function, and do the same, just do what I did right here. And that is your lecture for Tuesday, November the 3rd. So I hope you guys will work these homework problems diligently. If you have a question or problem in any of them, don't understand what's going on, take a picture of your work, attach it to an email, and send it to me. And as I'm touring Connecticut and Boston and places like that, I'll take time out somewhere in there to look for your emails and send you an answer. Y'all have a great time with that.